morning, everybody. I'm Marshall Curtis, mechanical engineer.
I'm Chris Patterson, mechanical engineer.
I'm Ethan Shudak, electrical engineer.
I'm Jacob Stash, mechanical engineer.
Our advisor is Dr. Carol Bedore, and we're Retrocruise.
So for an introduction to our project, the Retrocruise design is both a cruise control and speedometer correction system that is designed specifically for domestic classic cars. We do this through the use of modern electronic components as well as an unobtrusive mechanical design to create a safe and useful standalone system. There is nothing like this currently available on the market, so we aim to fill a niche in the classic car world. Some goals we've set for this project since the beginning have been an easy install and use for the operator. We wanted our speed display to accurately display the vehicle's speed at any given time within 2 miles per hour. We want our cruise control system to be smooth and functional, and most importantly, we want our end user to be safe operating the vehicle.
With those goals in mind, it's important to cover some of the ethical considerations for our project. The first, NSV code we found in section 1.1 states that safety will be held paramount. This again emphasizes our need for extensive testing and multiple fail-safes to be effectively implemented into our system to ensure the end user and others on the road are safe. The second NSP code we chose can be found in section 2.2.8 and states that engineers should only undertake assignments within their qualifications. In combination with our now 4 years of school here at Wilkes, we all have experience working on modifying cars and feel like we are well qualified to go through with this project. Moving on to our work breakdown structure, we decided to break it up into 5 main categories. A lot of our time this semester was spent working on making adjustments to the mechanical and software sections, while also focusing heavily on testing to ensure the product is safe and consistent. Moving on to our schedule, it is broken down into the deliverables for senior projects 2 and shows a timeline of when we begin testing and finalizing our prototype and design.
So for a brief overview of our entire Retrocruise system, in the top left you can see our under-dash box and its magnetic lid with its various inputs and outputs spread out. In the top right you can see our speedometer motor mount attached to the back of our test speedometer. In the bottom left you can see our servo motor attached to our test carburetor. And finally a general overview of our system zoomed out for scale purposes. Now our underhood components have always kept a very similar design, but with slight changes across iterations. We began with a simple bracket that can bolt to any quadrijet carburetor. This design allows for both x-axis and y-axis adjustment of the servo motor position. We found that the thickness of this bracket could not hold our selected hardware, so we needed to add some wall thickness for our final prototype model. We also found that the 20 kilogram servo motor was not strong enough to open our carburetor all the way, so that needed to be solved as well.
So moving on to some of the problems we had with the servo motor and how we solved them. Initially, we had done our testing with an Arduino Uno, which provided a signal voltage of 5 volts, but the ESP32 we were using for our final prototype only supplies 3.3 volts. This meant that when we used the 25 kilogram servo we tested with, it was unable to fully open the carburetor secondary butterflies. To solve this, Ethan built a level shifter circuit to set the 3.3 volts up to 5 volts to power the servo. When we used the 25 kilogram servo at the 5 volts, it was still pulling some unwanted current, so we needed to choose a different option. We tested a 30 kilogram and a 35 kilogram servo and found that the 30 kilogram servo was too strong as it offered a higher torque at 5 volts when compared to the 35 kilogram servo motor. This presented a safety hazard, which led us to choose the 35 kilogram servo motor as it offered less torque at 5 volts. This is a view of our final underhood prototype. You can see where the 1/4 inch steel adjustable brackets sit on the carburetor and where the 35 kilograms
Minimize potential user error. Finally, we were able to support our sensor wheel on both sides, as well as add a backing plate to it to limit the amount of adjustability that it has within that optical gauge, leading to cleaner, more accurate readings.
So as Marshall had mentioned, we had to move our DC motor outside of our under-dash box. This design change presented some problems of its own that we needed to overcome. Among these were issues with alignment, binding, grinding noises, speed display inaccuracy, the DC motor bogging down, and also connection shaft shearing. For our final speedometer motor mount design, we aimed to improve the consistency and robustness of the entire component. We inserted a lock nut into the ABS housing and attached it directly to the back of our test speedometer. We then inserted our DC motor directly into the back of it. For our binding and shearing connection shafts, we decided to print the connector out of a rubber-like TPU filament to absorb some inconsistencies. This is actually similar to a speedometer cable spring that is already found in classic cars already.
Controlling the speedometer came with its own set of issues. Starting with the electrical problems, the DC motor was pulling more than its rated current limit. This was currently was around 500 milliamps, and we were seeing an average around 450 milliamps with peaks up to 700 to 800 milliamps. The initial motor drive circuit didn't work and would actually invert the signal. So a low percent duty cycle would drive the motor at a high speed, and a high percent duty cycle will make the motor spin slow. On the software microcontroller side, I initially had issues generating a PWM signal from the ESP32 to drive the DC motor. And then mapping the duty cycle 2 miles per hour such that the correct speed would display on the speedometer was also a bit challenging. And PWM signal frequency and resolution are inversely proportional, and this problem will appear later. So for the solutions on the electrical side, we decided to drive the motor with 2 different frequencies. For the low speeds, we decided to use 13 Hz, and for high speeds, to use 10,000 Hz. The high current draw of the motor was solved mechanically once the motor was aligned properly and the TPU shaft was inserted to increase some dampening force. The motor only drew around 150 to 200 milliamps. And for the motor drive circuit, I decided to go with a simpler low side NMOS channel MOSFET to make it a little more simple. On the software microcontroller side of things, Marshall and I sat in the lab one day. I would type in a low duty cycle, see what speed it displayed, and then just increase 1% and write down what speed it then displayed and created a mapping from there. For our coding, I just found a lot of documentation and adapted to our system to what we needed to do.
Now moving on to our speed sensor testing. In order to convert the mechanical signal that we were taking from our speedometer cable into an electronic signal that our microprocessor could read, we had designed a sensor wheel. This sensor wheel pressed onto the stock speedometer cable, and on the other end had a wheel with 20 slots around its circumference. We were able to detect each of these slots through our optical sensor as a rising edge, and after 20 rising edges, we knew that we had 1 revolution of the wheel. Knowing the time over which this occurred allowed us to figure out our frequency of the wheel. This, in combination with other known vehicle factors such as the rear differential ratio as well as the rear tire size, allowed us to calculate the table shown here. Here you're seeing the wheel RPM as well as the mile per hour that equates to, as well as the drive shaft RPM and frequency. This drive shaft RPM and frequency are equivalent to the frequency that we were seeing through our optical sensor and allowed us to conduct our testing. Here you see that we were able to output a set RPM in our drill to simulate what the speedometer cable would be outputting to our signal. We were then able to see our readings on our microprocessor, and then we're able to accurately output our mile per hour and our frequency through the oscilloscope. We then conducted 3 additional tests on top of this, ranging from 15 miles per hour to 71 miles per hour to simulate what we would consider reasonable driving speeds that you might regularly see in a classic car. Throughout all of these tests, we never saw a variation in our speed off of our actual speed greater than 1.5 miles per hour.
So the way the speedometer works is it literally maps speed for your frequency signal to a PWM signal varying in duty cycle. I then found these min and max frequency using the Excel sheet Marshall just talked about. I found the maximum frequency to be around 1700 Hz or around 120 miles per hour. This then gets mapped to its corresponding duty cycle range. As I said, there's a low speed mode which operates at 13 Hz and has 13 bits of resolution. Then there's a high speed mode which operates at 10,000 Hz and has 10 bits of resolution. Then I use this equation shown below to find the corresponding amount of levels the microcontroller needed to count to before it would switch the signal off, generating a PWM signal varying in duty cycle. As you see in the video on the right, you can see it switch from the 13 Hz to the 10,000 Hz. The DC motor was driven at its rated 6 volts and can spin up to 3,000 RPM. And since the duty cycle varies the voltage seen by the motor, you can see an example of what the minute motor was spinning at. So for the PID and cruise control, I decided to use an open source library called QuickPID found on GitHub. The input variables to the object PID are measured frequency, your actual speed that you're currently traveling, your pulse position code, which gets sent to the servo to actuate the throttle, and your set point, which is measured in hertz. The PID the PID calculates its error every 20 milliseconds for 50 hertz, which is the same as a servo. I found if you made the PID calculate the error quicker, it would actually cause the servo to jitter and not be stable. The KPK and KD values were found as such, and the reason the KD value is 0 is because of sensor and save abilities and a lot of vibrations. The KD value would amplify these small fluctuations and cause the servo to oscillate and kind of not stay steady. This is the final circuit schematic. Some notable changes are in the bottom right-hand corner. You see the new level shifter circuit for the servo. Right above that is the upgraded motor drive circuit. And then another circuit that was added is a Zener diode that which takes a car's brake voltage of 12 to 14 volts and sets it down to 3.3 volts such that the ESP32 can read it.
There were 3 main safety features we implemented into our system for the user while using cruise control. Starting on the left, the user would press the cancel button at any time while using cruise control. The servo motor position would return to 0 and the throttle would be closed. In the middle is a video simulating our brake switch. To simulate the brake pedal being pressed, we touch the brake signal wire to the supply voltage, and that closes the throttle. Finally, on the right, if the system were to completely lose power in any situation, the servo motor would again return to its 0 position, ensuring the user is safe and back in control.
So this is a video of our full system overview. I'm currently using a testing circuit and an external DC motor to spin the sensor wheel, which simulates a car driving. I'm using a potentiometer to increase the speed. I'm going to get the speed set to around 60 miles per hour. Once it hits 60, Marshall will then set the cruise control. I'm going to decrease the speed a little bit. You see the servo turn on. I'm going to turn the speed. You'll see the throttle open, and I'm going to say remain below the set point. The throttle will continuously open because the integral term of the pig is gaining air, thus trying to force the output to go closer to the set point. I will then increase the speed past the set point. You'll see the throttle will go close, and I will drop back to below the set point. You'll see the throttle open again, and Marshall will then hit the cancel button, closing the system, stopping the system.
This is a breakdown of our budget for this semester. Our total cost ended up being roughly $329, and our unit cost was only around $74. It is important to note that we purchased everything out of pocket, as we wanted this project to be ours from the very beginning.
Now, reflecting back on our time here at Wilkes, we decided to look back to the initial goals that we had set for ourselves. Our first goal was to create a system that was easy to use for the end user and ensured an easy and quick installation. To accomplish these, we designed a 2-button system, which is very self-explanatory, and ensured that our system is installed with only 3 spliced wires into a factory wiring harness, as well as 6 additional nuts and bolts. Our second goal was to be able to display an accurate speed within 2 miles per hour from any range of speeds the vehicle may see. In order to do this, we conducted testing from 0 to 120 miles per hour and never saw our error exceed this 2 miles an hour. Our third goal was to be able to accurately actuate the throttle over cruise control, and while we were unable to test on the vehicle due to time constraints and some vibrational issues that we had, testing on the bench proved that we did get good results. Our final goal, and most important, was that we wanted to design a system that would be safe for the end user. As Chris mentioned, we did have 3 safeties, but it's worth noting that over the entire semester worth of testing, we never saw one of these safeties not work when it was commanded to.
Moving forward, we still have some big plans for this project after graduation. We've already discussed as a team about the use of a GPS-based speed sensor rather than relying on our mechanical wheel and optical sensor. We believe this would greatly increase our consistency as well as decrease some possible failure points for moving parts. We've also talked about using an AI-based neural network to gradually tweak our microprocessor code when it is fed some driving data.
The Retrocruise team would like to thank everyone for their attendance today on their Saturday morning. Special thanks to Dr. Bendars for his class coordination, Dr. Gore for advice and guidance, and Mrs. Stash for today's great event. With that, I'd like to say thank you.
Questions? I come to you first.
This is a simple one. First, there's 2 questions. So whose 1967 Pontiac GTO is that? That's gorgeous. What do you have under the hood?
Stock 400.
Stock 400, beautiful. Quad? You have a four-barrel? Yeah. Beautiful car.
Thank you.
What make, model, and years of vehicles was this targeted for?
Anything with a quadrojet that could be on it. We have intentions to expand anything with a Holly or Edelbrock, so at that point we're really at anything carbureted that's domestic. For right now, we're primarily targeting something between 1965 and up to the mid-80s.
So domestic?
Yes.
Yeah, so my dual-seated stronger carburetors won't work for it. Okay. That was great. I saw your calibration that you did for the speedometer and stuff. Is that why you put that in your microcontroller?
Yeah.
The table of basic?
Yep.
Okay. Was that difficult?
It was a simple, literally mapping function not on our Arduino documents. So that's why I needed the min and maximum frequency, because it then maps from 0 to 1700 hertz and maps it between. The code gets a little more complex because there's a switching frequency in there. So the low speed switches at around 225 hertz, which is around 15 miles an hour. Once it hits that point, it switches to the high speed mode and then maps the duty cycle from 21% to 66%, from 255 hertz to 1700 hertz. So that'll take you from the 15 miles an hour all the way up to the 120 miles per hour.
So go back to your schematic, please. Because you're doing PWM.
Yeah.
PWM, when a switching circuit like this is inherently noisy. Okay, so how are you fighting that noise?
During this project, I actually haven't seen much noise, especially on that, on the outside of the DC motor. But I know with the IRZ44N, it's a little bit of overkill for this project. So I don't think switching frequency, because we're operating at somewhat of a lower frequency, because Because I think their maximum switching frequency that they went up to is like 250 hertz until they saw like a decrease in the output. So we were well below that limit, so I didn't really see too much noise.
Yeah, I'd be curious when I turn my AM radio in your car on and you're running this thing, you're gonna hear the line.
Yeah.
I actually saw another issue with the buck converter. Since the buck converter operates at a higher frequency than the PWM, the buck converter is more likely to cause noise on the radio than the generation of the PWM signal on the
Yeah, so that's at the future work.
Yeah, sure. Yeah.
Okay, more questions?
Good job, guys. I go to slide number 18 or 17. One before maybe, where you were showing the different velocity that you were testing. I think that you test for 80, 50, and 70 miles per hour. Yes, this one. My question is like, are you expecting that the system is going to work properly for higher velocities, say like 80, 90 miles per hour, or is all this going to work for that range that you were testing between 15 and 70 miles per hour?
We've tested all the way from 0 to 120 miles per hour, and our system still stays within our 2 mile per hour constraint.
We elected to display these results just because they're what you typically see under driving conditions.
And also to increase the speed of the external DC motor, it vibrated a lot. We saw a lot of inconsistencies in readings. That's why we just put on there's a lot of vibrations and mess up the code. So I would say garbage in, please garbage out.
Very good job. Okay. So, especially the presentation was very powerful, so good job on that. But I do have a few questions. And the first is, I really hope you guys, so you did the controller design purely based on, you even used the package. Did you ever try to do a little bit of modeling of the system so you can get learn that so you theoretically understand what are the gains you should have so that the system would be stable? I really hope you could have studied the stability of the system a little bit. It's not just empirical. And this works, and that's because it works.
We were hoping to, but because vehicles range in weights, so the PID controller would actually be different based on the vehicle that it's going in. So we didn't feel that modeling would be beneficial to us because the PID constants would change with the vehicle, which is why we're hoping to go to an AI system that kind of learns the vehicle's needs as it drives.
Okay, so tell me, how did you, in the process of when you were choosing those gains, and how did you get to there? Did you ever run into an unstable system?
Yeah, plenty of times. What I did, I kept the KI KD 0, and then I increased the KP until I saw oscillations. And then I just kind of messed with the parameters and saw what worked best. But in terms of getting the final parameters, what I actually did is I hooked up my sensor wheel to a spin oscilloscope, and I actually found what frequency would drop in terms of miles per hour. So I found that for every mile per hour, you drop in 14 hertz. So I made a range of like 50 hertz, saying, okay, this is around a drop of like 3 miles per hour, we'll say. And I watched the servo output. If I saw the throttle output pin the throttle and you barely lost any speed, obviously your KP turns too high, so I would turn the KP, turn it down. Once I got the KP term to slowly open to a set, kind of use engineering intuition, how okay, if I see the throttle open this fast, what's gonna do to the car? I added the KI term to reduce the steady state error. So what I would do is I would decrease the speed a little bit, make it see the throttle open, and I would turn up the speed a little bit and make sure that the servo goes closed right at the set point. So in terms of tuning, it was kind of arbitrary, but the way I went about it was more of I wanted to be within 1 or 2 miles per hour. So I made sure that if the error was larger than 1 or 2 miles an hour, I made sure that it opened the throttle pretty decently to bring it back up to that set point. And once you got to that set point, the throttle should close. And I kind of just watched for when it did that and found KP and KI terms based on that.
So the KP term is really just like a noise and it doesn't work very well.
And that's why any vibrations, any fluctuations, you would see the servo just sit there and jitter. And even when you increase the error, you'd still see it jitter. So you would be pretty much pulsing the throttle, which wouldn't be good. So that's why we're trying to move to a GPS-based speed signal, because it could be a little more steady and a little less vibration, or a little less affected by vibrations. So it would be a little steadier for the pit control. But I know with a Type 2 system, what the car will be, the KD term is quite necessary, because if you're going downhill, or you're going up the hill, you don't want to see a quick response. You kind of want to have a nice slow response going up the hill. So it would kind of just depend on what, like when we get it onto a car, that we need a better sensor to tune the bit more accurately.
Did you observe the statistic error goes to 0? It does goes to 0. Okay.
And it was a range between like 0.3 to 0.5, anywhere in that range. It seemed like it would go back to error, or like the set point. Any values higher, it would actually get saturated, and the throttle would remain open. So,
Is there a way for you to collect the like speed and the, I mean, for your project, it would be really powerful if you can plot the command speed and the actual speed and really, is there such a plot? You see what I mean? Like,
yeah, if you go to the appendix, the video might be in there.
Yeah, I think it is.
Yeah, so this is kind of me like tuning it. You see the 14 hertz and the 1 mile per hour drop.
One video that.
and that's okay.
Yeah, but if this was a serial plot of the servo position code, the set point, and the current speed reading. So you would see, if I drop the set point below the set point, you would see the servo position increase. And then if I go above the set point, you would see it go back to 0. And then if you got the set point exactly on the set point, you would see the servo were getting closed. Maybe because of vibrations, the sets, like the actual speed would be like fluctuating around the set point. So you would see that throttle little blip at the bottom because it's kind of oscillating between the set points.
Like how much, if you go from like a 10 to like 70, how much does it overshoot?
It shouldn't, because you set the speed, and so you're continuously setting, like going like at that speed. But if you're going up a hill, the PID controller actually should react a lot quicker, because I'm kind of using the PID measuring hertz, not miles per hour. So with the 14 hertz range, the PID control could actually react really quickly. So I was just trying to get, so if you're going up the hill, you start to see that set point, or your actual speed go below the set point, you want to see that throttle slowly open and creep open, and you want to just see it slow because you don't want to hit the throttle and accelerate quickly at the hill. You want to have like a nice slow acceleration on it. So I was trying to just aim at that as you're going up the hill, you're obviously going to be decreasing speed, but that throttle, as you saw in the video, will increase its steps, increasing the throttle, therefore accelerating up the hill, picking up speed, and then getting back to that set point. So it shouldn't drop the miles per hour that like far, but without actually testing out a car and seeing the dynamics of the car, it's hard to tell.
Okay. That is a very good job. Okay. I'll give other engineers a chance to discuss this. Like, what could cause the system to make it unstable? Like, what could make it unstable?
So any vibrations with our sensor wheel would cause the reading to come poorly, so the servo motor would jitter.
Did you observe that during the experimental testing?
Yes, a lot. So
And when that happens, what did you do?
So
yeah.
that kind of went back to our final box design, where we braced the sensor wheel on both sides of it to kind of keep it centered between the optical sensor. Here you can see it's just kind of in on one side, and we always kind of thought of how are we going to hold this sensor wheel like firm in space, because the speedometer cable that would attach right into the back of it had kind of slack in it, so it could move in and out. And with that secondary bracing that we added to the sensor wheel, we saw a lot of our inconsistencies kind of go away.
Okay.
On top of that, the shaft that came off the DC motor, we were initially printing in hard ABS, and that was not allowing for any vibration to be absorbed. So that's why we did switch to that TPU, because it absorbed some of that vibration, like the OEM spring cable did. So the original cable is tightly on spring to absorb those vibrations.
Okay. Just one. You don't have to answer this. Just one quick comment, because pulse width modulation is a big range. It went from like a 10 kilohertz to like 13 hertz. Why is that? Why is such a wide?
So initially we had motor issues driving the motor at very low speeds. So below like 20 miles an hour, the DC motor would actually just stop. So the one day when Marshall and I were in the lab testing, I'm like, let's just try like low frequency and see what happens, and just kind of pulse the motor, just because the way the speedometer works is Mark, he can explain a little bit.
So going on the speedometer, we initially thought that it was going to be a linear mapping, that we were going to be able to linearly correlate speed to our input frequency. We found that we're unable to do that. Just the speedometer actually works based off of a magnetic signal acting against the clock spring. So that caused us to be unable to drive at low speeds. So our attempt was to just simply pulse it at a lower speed and a lower frequency. So we were at 10,000 hertz. That was what we were trying with initially. So we went down to 10 hertz just because it was a simple.
So you switch based on the speed command?
Yeah, so below, when you're displaying below 15 miles per hour on the speedometer,
I see.
it would stall the motor if you were at 10,000.
I'm just not a bit surprised to be such a huge difference to go, for example, go from 14 to 16 or so. I mean, there's
So we did testing on that, and that's obviously.
actually works in both domains.
Yeah,
Right?
so we did testing from, I believe it was 7 hertz all the way up to 20 hertz for a low speed. We found 13 hertz was almost the only frequency that we were actually able to maintain that plus or minus 2 miles per hour. And then we were able to switch that frequency up to 10,000 hertz, and that worked for us from the beginning, so we didn't actually extensively test that. We didn't have any issues with it right off the bat.
Okay, all right, thank you.
Okay, so great job, team, to a successful project. Thank you so much.